Question 20, we have a system of differential equations. When you have a system like this, you can look at the coefficients -1, 7, 2, and 4 and make this matrix of coefficients to write it as a matrix equation. Remember, matrices multiply like across down, so if you multiply across down here, -1 gets multiplied to x, 7 gets multiplied to y, and if you add them up, you get -x plus 7y. And if you do across down for this one, 2 times x, 4 times y, so you get 2x plus 4y, you get the second one. So you get this differential equation in matrix form, which is same as the system of differential equation you had before. Now, so to solve this, you need to know the eigenvalue and eigenvalues and eigenvectors of this matrix, the coefficient matrix. So let's do that. How do you do it? You subtract lambda from the diagonal, and you take the determinant. Determinant gives you something like this. You have to do AD minus BC, right? This times this minus this times this. You get this thing, and if you set this equal to 0, you get two solutions, lambda equal to 6 and lambda equal to -3. For each case, you have to find the corresponding eigenvector. So what you do is you take this 6, plug it back into this here, and you get -1 minus 6, which creates -7. Over here, 4 minus 6 gives you -2. And by the eigenvector, I mean a vector. If you multiply by this matrix, you get 0, 0. So in order to figure out what gives you 0, 0, you have to, again, do a cross down to figure out what that is in terms of writing explicitly. So you get -7 times A plus 7 times B. And you have to have 0 on the right side. And it's easy to see that if you have 1 and 1, it gives you 0. So 1, 1 is the eigenvector. So that's the eigenvector. Now for lambda equal to -3 case, if you do -1 minus -3, you get -1 plus 3, which is equal to 2. So you have 2, 7. And the same thing here. And then once again, if you do a cross down, you get 2 times A plus 7B, and that has to equal to 0. And when it's not so clear what to use, what you can do is you can switch these two around. So put 7 here and put 2 here, and then just negate one of the numbers. You can either choose to negate the 7, or you can choose to negate the 2. At the end of the day, the answer will be the same. Let's choose this one. So I got A equal to 7 and B equal to -2. And we chose the eigenvector to be this one. Now once you have the eigenvalue and the eigenvector, then what you do is you write down the general solution as C1 times the eigenvector times e to the eigenvalue times t. Same thing here, C2 eigenvector e to the eigenvalue times t. So that's what you get. Now, another important thing that you have to know is that sometimes I explicitly ask you to find out what x of t is, or maybe what y of t is. And when you write it in this form, and you don't know how to go from here to there, you're going to get stuck. You wouldn't know what to write. So here's how you do it. You multiply these together, so this is really equal to C1 times 1 times e to the 6 t, and C1 times 1 times e to the 6t, right? That's one vector. Plus, the next one is C2 times 7 times e to the -3t. And this is C2 times -2 times e to the -3t. I don't have room here, but you know what I mean, right? So when you add these two, you get the first top element as this plus this, and therefore you get x as this, okay? And you can do the same thing for y, so you get this as your answer. So the important thing is you have to know how to write your answer in both ways, in this form and also in this form. Question 21. Here is another similar question. This time you're explicitly given the matrix form. But one thing in addition is that you're given these initial conditions. So if you're given this initial condition, how do you solve it? That's the question. All right, again, the same thing has to be done. You subtract lambda from the coefficient matrix, take the determinant so you can find the eigenvalues. This time we got 6 and -2. Plug the 6 back in here. 1 minus 6 is -5. So again, this here means it's -5a plus 3b equal to 0. You switch these two around, so you have 3 and -5. I guess we like positive, so let's negate this one, so you get 3 and 5. So you get 3 and 5 as your eigenvector. For lambda equal to -2, do the same thing. You get 3ab, which means 3a plus 3b. You could switch these two around, which is same as 3, and use negate one of them. So 3 and -3 could be a possible answer, but what's better is just divide everything by 3, then what do you get? That's same as a plus b equal to 0, right? And that's very easy to solve. You just have 1 and -1. Okay. And because you need to figure out what C1 and C2 are later, it's actually easier if you find the simplest number. If you use 3 and -3, it's not impossible, but you still the numbers will come out uglier. Okay. All right. So here's the general solution. Again, the same thing. C1 times the eigenvector times E is the eigenvalue t. C2 times eigenvector times E is the eigenvalue t. And then to satisfy the initial condition, now you have to plug in t equal to 0 both sides. Okay. When you plug in t equal to 0 to x1, x1 of 0 is 1, that's what you're given. x2 of 0 is -2, that's also given. And then on the right side, if you plug in t equal to 0, you get c1 times 3, 5, because e to the 0 is 1, they just simply disappear. So times 1 is nothing, right? So you just have this. Now you have to read what this means. It means this is a 3 times C1 and 1 times C2, right? C2. And then what? 5 times C1 and -1 times C2. And these two are added together. So if you add the top and top, matrices are added with the corresponding element. So this adds to that one. That gives you the top one, which is 1. So you get the first equation here. And the next equation is this one. And you just have to solve this. Well, easy way to do this is if you write it like 1 equals to 3c1 plus c2, and -2 is 5c1 minus c2. If you simply add them together, these two add up to 0, these two add up to 8c1, and then this one is 1 minus 2, so it's -1. So if you solve for c1, you get -1/8. And then you plug this into either one of these to solve for c2. And if you solve for c2, this is what you get. And once you get it, you plug them back into our general solution, and this is what you get. Okay. Now, since the original question was posed as a matrix form, it's okay to write your answer in matrix form. But if this was given as a system, for example, if you were given like x1 prime is 1x1 plus 3x2, and x2 prime is 5x1 plus 3x2. If it was a system like this, it would be better if you can actually write down x1t and x1t and x2t separately. For example, you can write down x1t as -3/8 e to the 6t plus 11/8 e to the -2t. So that could be a good way to write down the solution. All right, now let's see. Rewrite the following differential equation into a set of differential equations, also put it into matrix form. Here is what we have, and the goal is to write this as a system of first order equations. Okay. Differential equations. The way you do it is you introduce y1 and y2 as y1 is y, y2 is y's prime. So you take y and its derivative, you assign it to two separate functions. Now, if you assign it like this, of course, there's a relationship between these two functions, which is that y2, if you take the derivative, it's not here, okay. If you take y1 and if you take the derivative, that's like taking the y's prime, which is equal to y2, okay. So that's one relation you automatically get immediately after this, that y1 prime is equal to y2. The next thing is that y2 prime, since y2 prime is y's double prime, you can rewrite this replacing this one as y2 prime, and this one will be replaced by y2, this y will be replaced by y1, and if you do that, this is what you get. So above equation here becomes this. And then you put these, well, solve this for y2, so y2 prime. So if you solve this for y2 prime, you get y2 prime. This goes to the other side, you get negative 3y2. This goes to the other side, it's plus 4y1. And you have one equation, another equation, you put those together, and that is your system of equations. How about the initial conditions? Well, y of 0 equal to 1 is the same thing as y1 of 0 is 1, because y and y1 are the same thing. And since y prime is same as y2, that's y2 of 0 equal to negative 2. So those two are the same thing. And you can also change this into matrix form. Just write this as, think about this as 0 y1 plus 1 y2. So it's 0, 1, 4, negative 3. That's the coefficient matrix. And your initial condition can also be written like this. Okay, so that's how you change a second order differential equation into a system of first order, and also this. Okay, number 23. Determine the eigenvalues and associated eigenfunctions for the following endpoint value problems. Alright, so this is a special case of Sturm-Liouville equation, and we talked about this. It's always this equation, y double prime plus lambda y equal to 0. The actual Sturm-Liouville is much more complicated than this, but we'll only do these types. So the equation will always be of this form. And there are two variations that we're going to do. One is where the value itself is 0, or another one is when, like this one, where y prime at the endpoints are 0. Okay, going back, how do you solve this case? Well, in either case, you should always think about the case where lambda is 0 or positive or negative. But there's a theorem which says that lambda negative will never happen. You never get eigenvectors in this case. So thanks to some theorem, you can just do lambda equal to 0 and lambda positive. Those are the only things that you have to consider. When lambda is equal to 0, what does that mean? That if lambda is 0, you get y double prime equal to 0, which means if you integrate both sides, you get y prime equal to a constant. And then if you integrate again, you get y equal to ct plus another constant. Then I guess since these two constants don't have to be the same, I'll just name this one as c2 and name this one as c1. Okay, so that's what I did over here. Now plug in the boundary conditions. Y of 0, what's y of 0? If you plug in 0 here, you get just c1 by itself, right? But since this has to equal to 0, you're forced to say that c1 has to equal to 0. But then, what is y of 4? If you plug in 4 here, c2 times 4 plus c1, that's what you get. But since c1 is 0, you have c2 times 4 equal to 0, which again forces the c2 as 0. And going back, if you plug in 0 and 0 here, you get y equal to 0, which means it's a trivial solution. What's a trivial solution? Trivial solution is when you have y equal to 0. And those are not good. Eigenfunctions are functions that are not trivial. Now for lambda greater than 0, we can write down the characteristic equation. The characteristic equation for this is r squared plus lambda equal to 0. If you move the lambda to the other side, you get negative lambda. And if you take the square root of the negative gives you I, and you have to take the square root of lambda also. So this is what you get. And for this solution of the characteristic equation, you know that the general solution is, well, it's in general, it's a plus bi gives you the e to the at cosine bt was some constant here plus c1 C2 sine BT, just like this. But since A is 0, you don't have anything here, so you should think of it as 0 plus minus lambda, square root of lambda. So e to 0 is 1, so you don't get this at all, and you only get this, okay? With b being square root of lambda. So this is what you're getting. And then again, plug in y of 0, and then you get c1 equal to 0. And then once you have c1 equal to 0, plug it back into our original. So if c1 is 0, what do you get? You end up with y equal to c2 sine lambda t. So that's what you get. Then think about what the next endpoint condition is saying. Y of 4 has to be 0. So y of 4 is c2 sine square root lambda times 4. I'm replacing t by 4 here, and that has to equal to 0. Now you have two choices. When two things get multiplied to create 0, it's either that the first one is 0 or the second one is 0. But c2 equal to 0 is not an option for us, because if c2 is 0, if you have c2 as 0 and c1 as 0, then you end up with y equal to 0, which is a trivial solution. You don't like that, okay? So your only choice you end up with is this. See, if you're looking for a non-trivial solution, then you need the sine of square lambda times 4 equal to 0. Now, because the sine function, if you recall the sine function, what's the sine function? It's like this. And it's 0 as 0, pi, 2 pi, 3 pi. Whenever you have some integer times pi, you have the crossings, right? It crosses the x-axis, so you get 0. So you know that if this is, in order for this to be true, it has to be true that this thing inside must equal to n pi. Now, if you solve this for lambda, you get lambda equal to n squared pi squared over 16. And since we're assuming that lambda is strictly greater than 0, n can't be 0, it has to be 1 and afterwards. So here we have this with n equals to 1, 2, 3, so and so. And if you plug that back into here, then here, right here, y is c2. c1 has to be 0, and so you get this. If you replace lambda by this thing in here, you end up with y being this. Okay. And this is the general eigenvector for the case lambda equal to n squared pi squared over 16. But usually you just want one such eigenvalue. So we'll just normalize this by taking c2 as 1, and you get this. So you get this as your eigenfunction, and this as your eigenvalue, with n being 1, 2, 3, and so on. Right here it said where n is any positive integer, it's the same as saying this. Okay, positive integers are 1, 2, 3, and so on. Okay, so that's what you get. One thing I should have said before is that since lambda equal to 0 only gives you a trivial solution, we know that that lambda equal to 0 is not an eigenvalue. Okay, so that's why you should have n starting from 1, 2, 3, and afterwards. Now let's see what happens if you have the derivative equal to 0 at the endpoints. So again, when lambda equal to 0, you can solve. Again, you can solve for y like this, and and since y prime is just c2 by itself, when you plug in 0 or 5, you get c2, right? See, y prime equal to c2, this means it's a constant function. What does constant function do when you plug in values? It always gives you the same number, okay? So whether you plug in 0 or 5, you get c2. And since c2 is 0 and c2 is 0, and you don't get any condition for c1, right? So you have this as a non-trivial solution as long as c1 is not 0. So non-trivial if c1 is not 0. Okay. All right. For the case lambda greater than 0, same as before. You have this solution. You differentiate so that we can again plug in the endpoints. Again, we have endpoints that forces one of the coefficients to be 0. Here, see, because we are assuming that lambda is positive, this can't be 0, so you're forced to have C2 as 0. If C2 is 0, then if you plug in 0 here, you end up with y equal to C1 cosine square lambda t. And then again, if you plug in y prime of 5, since C2 is 0, you don't get C2 at all. You only get this part. That has to equal to 0. And again, C1 can't be 0. And since this is positive, the only way that this entire thing could be 0 is when this part is equal to 0. When that part is equal to 0, again, you know that the thing inside should equal to n pi. Solve for lambda. You get your lambda values from n equals to 1, 2, 3, and so on and so on. And then if you replace this lambda by this thing in here, right here, C2 is 0. So you have y equal to C1 cosine. Square root of lambda is n pi over 5, so you get n pi over 5 times t. Okay, so that is your y of t. And then y of t is cosine n pi t over 5, and lambda equal to n squared pi squared over 25, where n is any non-negative integer. What does non-negative mean? It means it could be 0. So this is another way of saying that n is 0, 1, 2, 3, and so on and so on. Okay. Now, if you compare this to the previous one, previously we had n equals to 1, 2, 3, and here we have n equals to 0, 1, 2, 3. So what's the difference? Well, here in the case 1, we did get an eigenvector. If there is an eigenvector, since this is non-trivial, we can think of this as eigenvector. And if this is an eigenvector, then n equal to 0, or actually lambda equal to 0 is an eigenvalue. Okay? And that's why when n equal to 0, you should take this as one of the possible eigenvalues. Now that brings into the question, well, when lambda is 0, isn't the eigenfunction different from the other case? But if you plug in n equal to 0 here, you'll notice that cosine of 0 is 1. And indeed, when C1 is 1, you do get y equal to 1 as a eigenfunction, right? I mean, y equals to 2, y equals to 3. They're all, any constant function that's not 0 is an eigenfunction for the case lambda equals to 0. So y equal to 1, that's one of the eigenfunctions among them. So that's perfectly okay. So good thing is we didn't have to treat these two cases separately. We can just write everything at once. Just say n is 0, 1, 2, 3, and just write this, and that automatically includes the case 1. So it works very well for us. Question 24, show that the following endpoint value problem does not have a solution. So if you had this and you had y of 0 as 0 and y2 pi as 3, you have to show that it doesn't have a solution. Again, write down the characteristic equation, solve it, you get r equals to 0 plus minus 4i. If the real part is 0, you know that the exponential term doesn't appear. So this is what you get. It's cosine of bx, where b is 4. So that's what you get. And then, and then we use the endpoints, right? So y of 0 equal to 0. How do we do that? That means that we have to plug in 0 here and 0 there, which gives you c1 times 1 plus c2 times 0. And then since that has to equal to 0, we end up forcing that c1 as 0. If c1 is 0, you can plug it back in and you get y as c2 sine 4x. But if y is c2 sine 4x, then you have y of 2 pi as c2 sine 8 pi, but sine 8 pi is 0, so you're forced to have 0. That's not good because we want y of 2 pi to be 3, and that's not the same as 3. So there's a contradiction. Okay? Once you have c1 as 0, it's impossible to make y of 2 pi anything else than 0. Therefore, there can't be any solution. Now, one thing to say is that since there is no indication of what variable is y a function of, you could have solved this assuming that y is a function of t. So you could have written your solution as y of t as c1 cosine 4t, and that would be perfectly okay.